So I was studying a little bit of physics, and I thought I would do a little bit of a proof, and a little bit of relationships between the horizontal velocity, the height, and the displacement. And so what I want to start with is I want to do some some advanced physics, and this is for all those people who know this horizontal projectile motion. But if you don't worry about it. This is just for the advanced, for people who know this, and I will do some basics and fundamentals of physics in future videos. So what I have here is horizontal projectile motion. I have a graph right over here where the x-axis represents the horizontal distance and the y-axis represents the vertical height where you could see h and d. And we have this platform right here. Let's say this is a type of building of some sorts, and it's at height h. We're not going to say what it is. I'm just going to say this is height h, and we're going to throw it off with a horizontal velocity of Vx. And so when you throw it off horizontally, it's going to travel some distance d. This is d. And you see g is the gravitational constant, which is equal to negative 9.8 meters per second squared. This is the gravitational acceleration. It accelerates down. That's why every time you throw something from like a window or something, it's going to fall onto the ground because there's gravity. So with this out of the way, let's start talking about this. So what I want to talk about and what I want to emphasize first is that d, which is the distance, depends d depends on the horizontal velocity. And that makes sense because if the the horizontal velocity, which is right over here, if the horizontal velocity, which I will, shade in orange, if the horizontal velocity were to increase, then of course d will increase. D is going to increase because you're going to throw it faster, you're going to throw it harder, but horizontally it's going to increase, it's going to go even even further than this D. So the bigger the horizontal velocity, the bigger the distance. Something else is that t also depends on h. And what is this t? Well, let me write it first. So as the height increases, as we make a bigger building, when you throw it again, the time it stays in the air will be longer before it hits the ground. So t will increase as the height increases. And the formula that we use, d depends on the horizontal velocity. We use the formula d is equal to the horizontal velocity times the time. So this is our formula that we're going to use, and we're going to use it after we solve for time in another way. So we're going to go down here, going to draw an XY plane, but they're going to stand for different things. So we have the y-axis right over here, and we have the x-axis right over here. And the x-axis is the time, which is in seconds, and the y-axis will be the velocity, which is in meters per second. So we have launched this projectile, this thing, this red dot, I guess you could say. And so it's the velocity, the initial velocity is going to be right over here at 0. And so we're going to label that as VYI, which stands for the initial being I, vertical velocity, which is VY, right? So the initial vertical velocity. And so we're going to go down a little bit. We're going to be accelerating down due to the gravity. So let me draw the line for that. And so it's gonna hit the ground at a certain time t right over here. And so this part is t. I'll label this part in blue. And right before it hits the ground, it will have a certain vertical velocity, and label that let's label that as VYF. That is the final vertical velocity. And we know that the acceleration is negative 9.8 meters per second squared. The meters per second right over here, the velocity, which is going to be the rise, over the run, which is seconds, meters per second squared. Does that make sense? That this slope right over here would be negative 9.8 meters per second squared. And we know that h is the area under the curve. H over here is going to be the area under the curve. So what we want to do is we want to solve for the triangle right over here. So the area under the curve right over here we would like to solve for. We are interested in solving for that. So H is our area, and that's going to be equal to, and an area of a triangle is always 1/2 times the base times the height. So 1/2 times t times the height we'll say is, well, we have VYF minus VYI. That's the height right over here of this. So if we divide both sides by t over here, we're going to get h over t is equal to 1/2. And I'm going to keep this t over here. I'm not going to cancel this out. And you'll see why in a second. 1/2 times t times, and in parentheses we have VYF minus VYI. And I'm going to put this over t. Now we didn't do anything. We just divided both sides by t. That's normal. But now what? Well, you should know that gravity, and I will do this in green because that's what we have here over here. Gravity is equal to v, which is the velocity over the time, right? That's the gravitational constant. That's the gravitational acceleration. So what we have over here, we have the same thing. We have v over t. We have vyf minus vyi over t. This is a velocity over time. So what we can do is just substitute this. This is v over t. So this whole thing becomes g. So this is going to be h over t equals 1/2 t times the gravitational constant, g. And so now when we solve for the time, that's what we want to solve for. We want to see how much time it takes. We're going to multiply this by 2 first, and we're going to, let's say we're going to multiply this by t to get the t over here. So we're going to multiply this by t, multiply this by t, and this is getting a little messy. I know, I'm sorry about that. And we're going to divide by g to get g over here with the things that we don't want. So now that cancels out, and that leaves us with t squared is equal to 2h over g. And so now when we take the square root to solve for t, you get t equals the square root of 2h over g. So now that we have this formula, and we have the formula up here that says that the distance is equal to the horizontal velocity times time, we can solve and get the big formula. So let me take this. So now that we have these two formulas right over here side by side, we can solve. We can put t over here into this t. We can put this t, which is equal to this, into this t right over here to get our formula as d is equal to the horizontal velocity times the square root of 2h over g. And that is our formula that relates the distance, the horizontal velocity, and the height with g being our constant.